Thank you. Thanks for inviting me, Ben. Before I start, and while I'm plugging this in, I just wanted to make a statement of the obvious. I mean, look at the number of people that are here from all across our industry, and just think what Ben, Justin, and the OVS team have created over the last, 8, 9 years now? At the time that they started, the thought of open source for networking was kind of a joke, right? At that time, nobody thought that it would take off. Nobody thought that this infrastructure, which is so important to all of our lives, would be turned over to what felt like a bunch of hackers, people who would be, in their spare time throwing a bit of code. And the world has changed in that time in a pretty significant way. And now I would say the problem is not whether we believe that there will be open source in networking, because all of the major infrastructure in the large data center companies now runs on open source switch operating systems and significant reuse of open source in other parts of their infrastructure. And so this really was one of the founding projects that got all of this started. So I'd like to start with a round of applause to these guys, because I think they've done an amazing job. Okay, I found the HDMI connector on my laptop. There we go. So, a few months ago, I was visiting a company in New York, and they were telling me about an experience that they had just recently had with a data center outage. It was one of those instances where everything came to a halt, applications stopped working, they were losing millions of dollars a minute or an hour or however they count. And so they assembled into a room, and you've seen this, teams of 2 people from compute, 2 people from storage, 2 people from networking. And within about half an hour, the people that were doing the compute, who were responsible for compute, were running experiments, trying to reproduce the error, isolate it. They had ideas, they had thoughts. They were trying to figure out what the problem was. The people from storage, yeah, almost the same, not quite as much flexibility. And the people from networking, they had ping and they had traceroute. And it's not surprising that within 3 hours, they still hadn't established whether it was a networking problem or not. Now, it turns out that it wasn't. But, as you probably know, about 60% of all of these major errors are caused by the network. But the networking people get about 80% of the blame, because we have such rudimentary, pathetic tools, generally, for being able to debug. Now, there are other people who own big networks who have developed their own, and we've all seen reports and accounts. You don't see much of the open source code for that, unfortunately, on how to do debugging of large networks, because it's a key differentiating capability. But I will put it to you that networking is in a pretty sorry state if we cannot go and modify and change the behavior of the infrastructure in order to be able to do simple things like keep it working, to see what the problem is, to run experiments. And this is where not only open source, but the ability to make open source available to those who run and operate networks, I think is really, really important. And so I've spent the last few years, a significant amount of my time on trying to figure out how we provide that flexibility and programmability to the networking industry at large. Because that SDN thing, it kind of gave us software for the control plane. But what about the forwarding plane? That which has been off limits for a long, long time. So most of what I've been doing is trying to add flexibility into the hardware switches, but clearly today at OVSCon, it's about the software switches or the software forwarding. And so I'm going to try and tie the two together. But I want to do this based on the experience that we've had so far, watching and observing people do this with physical switches, and then I'll try and tie that into some of the things that we might do or where we might go here with software switches. I would maintain that in order to be able to debug our networks quickly, efficiently, and in the same way that we expect in other parts of the IT infrastructure, that we need to be able to pick out a packet anywhere in the network and ask the question, why is this packet here? What was the path that it took in order to get here? What did it meet along the way? What was the congestion points that it found? What was the latency in every queue? Who did it share that queue with? Now, that's a harder question. You couldn't even begin to answer many of these questions today. But if you actually want to debug and control a network to the same extent that we do other parts of infrastructure, we should be taking these things for granted. And in fact, I think we should be crying bloody murder until we can do it in all parts of the infrastructure. So this experience is based on the particular experience to do with P4 running in the Barefoot Networks. I'm not here to talk about Barefoot. This is the only slide that's related to what they're doing. But I just want to say this as a setting of a context from where this came from. So it's one data point. There are other people that are using P4, notably Metronome, Intel, and others. And I'll talk a little bit about the connection with OVS a little bit later. So this is a 6.4 terabits per second switch that you can program, and this is the Tofino chip that you may have heard about that runs at 6.5 terabits per second. Okay. In this environment, the underlying programming model looks like this. So it's assumed to be a protocol-independent switch. And that's the basic architecture. Now think of this as the picture of the architecture like those RISC pictures that you saw in the mid-1980s. It's not a true representation of the actual physical layout or the number of stages or anything like that. It's a cartoon figure of what will fit on PowerPoint to show you roughly what's going on. But I put this up because it's the abstract programming model that initially inspired the P4 programming language. Okay, so think of P4 as a way of expressing the forwarding behavior that you would have in a switch, where the rough model is something like this. A sequence of match and action stages, just as you would do in a software switch or in a hardware switch, where each stage is identical and is then programmed to perform matches on headers, followed by actions, modify and update packets, and then send them on their way. So you can think of this as representative of almost anything that you would do, whether it's BPF or P4. So I'm not here to say P4 is better than BPF. They both are very complementary, and they both do very similar things. I'm actually just talking here from an experience with this kind of programming model. Just to take this one step further, in case it's not quite clear what this figure is, let me just show you a sort of a cartoony animation. Here's a packet arriving on one of the ports. Has a number of headers. That's what the little colored squares are. So the first thing is a parser has been programmed, and I'll show you a snippet of a program in a minute. A parser has been programmed to say, these are the kinds of headers that I'm expecting. These are the packet formats that I'm expecting. That is dictated by the programmer, just like you would see at the initial stage of OVS, and mostly in the kernel, where it's saying these are the packet formats that I'm anticipating. And so you would express those in a language that just looks like a bunch of header files that says this is what I'm expecting. The first job is to extract those. So in a software world, that's primarily typing those headers. And in a hardware world, it's physically extracting them and then putting them onto a bus or a pipeline. In this case, it happens to be a sort of many thousand bits wide bus where all these headers will be popped into these memory matching stages, followed by ALU actions that are performed upon them. So think of those ALUs as arithmetic and Boolean operations, things like insert bits for encapsulation and decapsulation. Remember that each of these stages is identical and knows nothing about a protocol. There is nothing in the description of these that knows what a protocol is, except at the time of programming. So it's a raw substrate, just like an FPGA would or a CPU would be, just a raw substrate that you then tell through the program what the protocol is. Each stage is responsible for transforming those headers. So that first stage might do something to end up with a different set of headers that it's manipulated. It might have decremented a TTL. It may have, I don't know, who knows, might have incremented a TTL. That's up to the programmer to decide. It may have inserted new headers. It may have deleted headers. It may have taken metadata that was associated with arrival times, queue occupancies, state that's private to the switch. And then it just go down this pipeline, multiple actions, memory match and actions being performed as it goes down. The reason for having multiple stages is pipelining gives us parallelism. Within each stage, you can have multiple matches and actions. That's kind of an assumption. So in a CPU world, this could be different cores, different threads that are performing match and action on different headers. And at the end, we have to put this back together again in order for the packet to depart. So that's the basic programming model. Actually, you know what? Is there anyone got any questions? They say, I have just no idea what you just described. Because everything else I say is not really going to make much sense. Anyone, just any clarification? Yeah. I don't mind interaction, it's fine.
So when you say parallel,
yeah.
multiple tables in each one?
So the question was, when I say parallel, do I mean multiple matches? Now, the assumption, the programming model is yes. A particular implementation, whether it's on a single-threaded CPU or a parallel chip, gets to decide, but yes, in general, the programming model is multiple. And so in this particular implementation I'm referring to here, it's dozens of different degrees of parallelism. The reason for that, one of the reasons for the parallelism is your friend here, apart from obvious in performance, is that in networking, when processing packets, there's surprisingly little serial dependency. And it took me a while to realize why this was, but the answer I think is kind of obvious. The reason that we have layers and encapsulation is for a separation of concerns. Separations of concerns, when done correctly, separate concerns and therefore allow for breaking of serial dependency. So there are relatively few. How many you actually need sort of depends on what you're trying to do, trying to implement, but of the order of a dozen to a few dozen serial dependencies in a rather complex system. Okay. So someone would write a program. You could replace P4 here with BPF. It really wouldn't matter. I think of them as interchangeable. Go through a compiler to compile down to map a program to configure this device to tell it what happens in each stage, what kind of matches, what kind of action. So when I say PISA, I don't mean a particular instance or a particular product from anybody. PISA is sort of owned by p4.org, which is an open source organization like OVS. And so it's just meant to represent an abstract forwarding model. The original description of the P4 language was in a paper that appeared back a couple of years ago now, and P4, for those who are interested, stands for Programming Protocol Independent Packet Processors, bit of a mouthful, hence P4. Here's a snippet of a P4 program. And again, if you were programming, I would argue that if you were using any language, one of your own creation, or using a modified version of C, you'd probably do it in a similar way. What are the things that you need? What are the elements that you need? You need some means to describe how the headers are going to be processed. A little snippet there that says about the header types that we're expecting, and they're actually listed by the programmer. Ethernet, IPv4, IPv6, things like that. And then after that will be the types of parser and the parsing actions that we would expect, which is basically telling us how do we find a header, the next header after we've processed the current one. Finally, we need to say what the process of processing a packet, what is the control flow through the switch. So when a packet arrives, in this particular case, we're saying parse it, then perform a particular match, depending on the output of that match, then go through the processing tree in a different particular path. Okay? So this is just one example. That first parser is used to dictate the parsing. Then the control flow and the table actions that are being defined are populated into those stages, ready for when packets start arriving. At the end is a deparser, which is just undoing the parser to assemble the packet back together again and send it on its way. And in most cases, this can just be deduced from the parser. It just says, this is what I need to do in order to put the packet back together again. Okay, so the job of the P4 program is to say what this pipeline can do, what it's capable of doing, so that when packets arrive, these are the way in which they might be processed. So it says you might see a rule that asks you to match on a particular field, and then the actions that you perform could be drop the packet, increment a value, encapsulate, depending on what that match is. So the programming includes all of those possibilities, and then the particular rule that is populated at runtime tells you what you actually do. So you might insert an entry, could be an IPv4 table entry, that says, if you match on this prefix, then drop the packet. Or if you don't match on this ACL rule, then drop the packet. And so those are instantiated at the runtime. So the control plane, or the switch operating system, or whatever you want to call it, is deciding what the switch actually does by populating at runtime with those entries. And it's putting entries into those tables. It's telling the, how it's configured, how the queuing and scheduling and things like this are configured. So you could mentally replace all of that pipeline there that I'm referring to as if it's a piece of hardware with the pipeline of OVS or VPP or anything which is doing processing of packets. Because let's face it, when we're processing packets, there aren't that many things that we do. We match on headers, we perform actions, and then we do a few more of those. We buffer them until the outgoing line is free and it's our turn to go, and then we leave. That's really all there is to it. And so being able to capture this in a way that is a common language that all of us know, as well as all of those who are using other switches, software or hardware, has a benefit, means that you can now envisage portable behaviors over different types of environment, and placing you in control of that infrastructure. Whether you are a seasoned kernel hacker, or a hardware designer, or just somebody that's interested in getting their network to work, which frankly is the goal at the end of the day. Things have changed a lot in networking over the last few years. This is what protocols looked like about 20 years ago. If you looked actually at the hardware switches, or even the small number of software switches, they basically had to decide based on an ether type whether they were dealing with IPv4 or IPX. That was pretty much what the limit was. This is what the flow graph looks like for a portion of a P4 program representing a top-of-rack switch. This is one at p4.org called switch.p4. It's done by a bunch of people who had built top-of-rack switches before. If you look in, that's just one portion in the middle. So things have changed a lot. So it's meant that it's very hard to design these things to be correct. So if you're whether you are writing kernel code for OVS or you're writing the Verilog that ends up inside a chip, it's really hard to get it right. And so having this programmability and this flexibility is an enormous win just to increase the likelihood that it's going to work, and you don't have to spend another $10 million to either replace a fixed function switch or spend another 3 to 6 months rewriting your kernel code. But at the end of the day, the thing that seems, going back to my earlier story, the thing that seems to make the most difference in my experience of watching people do this over roughly the last year and a half of starting to program is they want more visibility, they want more measurement, they want to have a better idea of what their network is doing. Everyone who runs a network knows how hard it is to see what's going on, and so everybody wants a better idea of what is going on so that they can then keep it going at all times. So natural questions to ask are, which switches did a packet visit to get here? Which rules did it match? What version of the switch rule tables were present? Which queue did each switch put our packet in? What was the precise queue occupancy when my packet arrived? How long did it wait? And whose packets did it have to wait with? There are two approaches that I've seen, and now I'm going to go through a little bit of a list, a sort of a laundry list of things that I've observed people doing. These are snippets of code that are written by users of programmable switches that have been written since about July of 2015. And this is both in a commercial environment and also researchers that I've observed. So in terms of visibility, and this visibility and measurement, I've seen a couple of examples. There's one that I refer to as packet postcards. And this is a way of trying to gather what happens to a packet as it goes through the network in order to be able to get greater visibility. So packet postcards is a way of just generating a small digest from every packet, sending it to a central repository, which is then going to give you the ability to analyze and maybe replay that network behavior. The great thing is you can replay the network history and understand and analyze what happened. The cons is you get a lot of extra traffic, but that's the trade-off that you have to pay. Here's what I mean by this. The server's at the end, green on the left, orange on the right. Packet is entering the network. When it gets to the first switch, it's going to send off a little digest that could say, here is the 5-tuple, this is the time that it arrived, this is the version of the software that it matched on, this is the entry that it matched on in the switch. And then they all get sent back to a central logging device, and at the end, the packet is intact. Clearly, we've generated a lot of traffic down to that device. You can see some commercial products like Cisco's Tetration that work in this manner. There are certainly other ones that do similar things. Another approach is in-band network telemetry. In in-band network telemetry, instead of generating a digest for every packet, we just add the information onto the switch, onto the packet. If you've got control over the data plane, you can potentially just add the information you need to the switch and then remove it before it gets to the application at the other end. So for example, in this case, we take the original data packet. We ask the switch to insert things like switch ID, version number, etc., as the packet goes through. When it gets to the end, we're going to take all that information from all of those intermediate switches and send it down to a monitoring device. Benefits, pros, cons. Well, in this case, the benefit is we're not generating any extra traffic. The con is we still need to be able to have that monitoring device at the end to be able to pick this out, and we've made the packets bigger in the middle. Everything's got a trade-off. These are two ways that you could do it. I expect there are a third, fourth, fifth, 100th way of doing it. The point here is both of those can be encoded as descriptions of packet processing by BPF, P4, any language like that, if the forwarding plane is programmable. You could do it in the hypervisor switch, you could do it in the top-of-rack switch, you could do it in a spine switch, you could do it in the WAN, so long as those have a means to describe that behavior. They're both very simple, they can both be done at line rate. We should be expecting these things. We should be taking these things for granted, in my opinion. As to which you use and how you use it and what you insert shouldn't be my decision as an academic. It shouldn't be a chip designer's decision. It probably shouldn't be a kernel hacker's either. It should be the person that's operating the network, who is frantically trying to get the damn thing to work. They should be the ones that say, this is what I need to see right now. Let me change that behavior. Let me update the behavior in my network in order to be able to see what I'm looking for. There's an implementation of one of those, both of them exist in P4 programs, just to show that this type of thing, once you can do line rate processing, whether it's in software or in hardware, then an expression of the matches and the actions are on the left, and then the particular action broken down, where it's showing the addition of the switch ID and the queue latency on the right-hand side, just as something that you could gather. Again, you would have to read that to figure out what's going on in detail there. My point is, you should take it for granted not only that you can make that change, but that it should be obvious and natural that if you need to see some behavior, see some parameter, see some state in the network, we should just take it for granted that that's something that's available. Another example that we've seen that people have used is tracking the path and the latency along that path as seen by individual packets in the data plane. So what we observed somebody do was collect the physical path and the hop latency of every packet using that same INT method. And then the last hop creates a small record connection just for the current active connections. That could be in hardware or in software. Records any sudden change in path or latency. They use it to quickly detect changes in the path latency so they can raise an alarm. And they do this at line rate in the data plane. Or they confirm the routing tables or the ACL tables are doing what they expected. So this path latency tracking is something else that somebody wrote and then contributed as a piece of open source code. Another one is something called connection tracking, which is tracking in the data plane. Again, could be done in software, could be done in hardware if the hardware was programmable. During congestion, so at the onset of congestion, triggers a switch, takes a snapshot of every packet, which is either collects and aggregates and then sends to a monitor, or just fires them off to a monitor, depending on how it's been programmed. Snapshot will contain the packet ID and the packet metadata associated with that packet. Again, could be from the kernel if it was a software switch, could be just the metadata associated with a physical switch. How would it be used? Well, to detect congestion incidents and then identify the events leading up to that congestion. So if I've captured all of these, then if I've stored them, if I'm storing a little window of these events, then I can see everything that led up to that congestion event, and then I can point to whoever it was that was the offender. Another one is layer 4 load balancing. This is one of the more common ones that I've seen. This is trying to offload what is typically performed by thousands of servers in large data centers today, which is incoming traffic is then load balanced across a number of internal servers. One of the things you need to do is to make sure that the packets that are being sent associated with a connection, all the packets belong to that connection go to the same server. If the server dies, then everything will be consistently moved, and if a new server is added, then all the traffic will be spread over those servers. Fairly simple operation, very common today for thousands of switches in data centers, thousands of servers in data centers to be dedicated to this device. Generally done as an application, running an application space, very, very expensive. If you could do this in the hypervisor switch, or in a software switch appliance, or in a physical switch that is programmable, then you can potentially wrap this into your plumbing, into the plumbing layer that is part of the network. After all, layer 4 load balancing is essentially just smart routing. It's just merely the decision of where to send a packet next according to some objective. So it potentially saves many thousands of servers. There's P4 prototype code available, and we've seen some demos of this. All sorts of things with custom traffic monitoring and filtering, general purpose stateful memory in order to be able to maintain state about connections. Use of Bloom filters for whitelisting, Bloom filters for statistical maintenance of consistency of where packets go, of where flows are sent to servers. Heavy hitter detection using sketch calculations, which could, again, operate inside a kernel. They can operate inside a physical programmable switch. Variants of NetFlow. All of these things that people have added because they had a particular problem that they wanted to solve because it was now available to them in their network. We saw somebody that was interested in doing a variant of source routing in a large data center network. It wasn't one of the MSDCs, it was a sort of a tier 2 data center where people were interested in doing flowlet switching between source and destination based on the congestion that was currently available in the network. So as packets would proceed through the network, they would want it to gather state using INT. They would then send over alternative paths just by doing source routing through the network. They can program the switches in order to be able to do that. And then at the end, they would just have information that would allow them to decide the best path. So there's a little bit of state that needs to be maintained or a little bit of code that would be maintained. At the source, it could be in the hypervisor switch. Along the path, it could be in the top-of-rack switches and in the spine switches. Wherever made sense, all done in a consistent language. Again, could have been P4, it could have been BPF. In this case, it happened to be P4. Scalable high-frequency OAM for people that wanted to do BFD automatically within the forwarding plane. Turns out, took 2 little pieces of P4 that were running in the pipeline. People that were doing various types of congestion control, where they were requiring explicit information out of the switches, current queue occupancy, current latency that would be inserted into packets in order to allow the end hosts to make better congestion control decisions. Things like variants of what Google have developed as Timely, where instead of having to measure the round-trip time from the end server and have to guess what the occupancy was on each of the switches, actually have the switches tell you, whether it's a hypervisor switch, whether it's the NIC, whether it's the top-of-rack switch, whether it is the aggregation switch along the way. And then you've got perfect information about the cause of the congestion, and you can then use that. Hosted destination tour admission control, where you essentially assemble all of the queues in the network as virtual output queues towards a particular destination in order to be able to push that decision back to the source. Flowlet switching as a means of doing decisions based on small pieces of flows, because in TCP you get this window behavior where you get bursts, and you can actually, as long as you get the delivery in order within one burst, then you can afford to have different bursts take different paths through the network because you're not going to get missequencing because those bursts have sufficient gaps in between. How do you do that? Little piece of code that runs in a switch, again, hypervisor switch, a NIC, a top-of-rack switch, an aggregation switch, in order to be able to describe what you would do. Heavy hitter detection. You're getting the picture by now, right? There's a lot of things that you start to see people do once they can program. Heavy hitter detection in P4. Here is the entire code for doing heavy hitter detection of deciding which are the elephant flows in the network as a simplified version with taking advantage of an internal internal capability. Key value stores in P4, people have suggested doing key value store caches for things like memcache, et cetera, inside the network, or Paxos in P4 for leadership election algorithms that was published earlier this year. So my point here is not to say, hey, you should run off and re-implement any of those. You can actually go and get the P4 code and download them. You could convert them to BPF if you wanted, or to C and then put them into a kernel. The point is here that we're talking about a rise in an expectation of those who own and operate networks. They're going to start to expect this kind of capability. And if we can get our act together, all of us, and have a common way of doing this, doesn't mean we necessarily need to all use the same language. P4 is clearly designed to allow it to be compiled down to very fast pipelines. That was one of its objectives. There's less of an issue inside a kernel or a software switch. But you can do direct automatic translation between BPF and P4. And so if they each have their use, then let's make sure that we can do that seamlessly so that we can have that operation where we can compile down to either or both, depending on what was present in our network, whether we're optimizing for a software switch or for a hardware switch. There's no need for us to waste time over the maintenance of two completely separate code bases. So with user programmable switches, I really think that we have a relatively few choices. We can continue with hand-coded C in the user space or kernel if we want. We can do BPF in the kernel. We can use user space C with something like DPDK, or we can do P4 compiled to user space or kernel. My preference would be if we can identify ways that we can have BPF-like code that gets put into the kernel, because we know that works, we trust it, it's an extremely efficient way to do it. You could have as a front end a description in any language, including in P4 or any other description language, that would then get converted into that code running in the kernel. And then be able to translate backwards and forwards between the two. Just think of the power that this would bring to those who own and operate networks if we can do it. Shabazz, who's sitting in the back, is going to give a talk this afternoon about something called Pisces, which is a protocol-independent software switch that will make it easier for adding functionality into Open vSwitch. We know that adding new protocol features is complicated in OVS. Ben and Justin have told us that many, many times. It takes a long time for new code to find its way into deployment. It requires domain expertise in both kernel programming and networking. How many people have an expertise in both? Relatively few. Wouldn't it be nice if we could change it so you only had to have the expertise in networking, which is quite likely a skill that people that run networks will have. They're much less likely to have a skill in modifying the kernel. When you modify OVS, many modules are affected, and it's a very long QA and deployment cycle. So the approach is to specify the forwarding in a different language. Again, P4, again, this could be BPF, and then compile to modify OVS. One question is, how do the performance change? This is native OVS expressed in P4. I'm not going to go through all the stages. You've all seen it before, I expect. These are the different the primary stages of processing that are in Open vSwitch. Let's look at a complexity comparison. Native OVS, the simple basic functions of OVS, is about 14,000 lines of code, and the typical method size is about 135 lines of code. If you express the same behavior in a language like OVS, which is merely saying, this is the parser, this is the match action sequence that we perform, and this is the control flow, then it's 341 lines of code. So it's a 40x reduction in the number of lines of code and a 20x reduction in the method size. You know which one you would prefer to do if you were not having to worry, if you were having to make a network work, you want one that's more compact, easier to check, one that perhaps you can automatically verify. Shabazz went through and made a number of changes. He'll go through this in more detail this afternoon. But by adding different capabilities like connection labels or tunneling and a tunnel OAM flag or TCP flags, you can see the difference in native OVS compared to OVS.P4. Could be as little as one file changed with just a handful of lines of code, a fraction of the code that would be changed. So code mastery, kernel code mastery in particular, no longer required. And Ben and Shabazz have been looking at how this might affect OVS in the future. So there's a number of different ways that we could do the user programmable software switches in future. So there's work in progress along these lines. If you want to learn more about P4, you'll find p4.org. It's something that's maintained by myself, Jen Rexford at Princeton, and Amin at Google. And it's an independent organization. Everything is Apache 2 license, as you would hope. There's a GitHub repo that has compilers and some programs. Most of the ones I just mentioned, you'll find in there as open source code. You're welcome to use it. You're welcome to convert it to another language if you want and use it there. That's absolutely fine. I hope people will do that. There's actually a developers day on Wednesday if you're interested. There'll be many of the same topics, more focused on programming towards more optimized pipelines than here, but many of the same topics. It's open to free to anyone that wants to join. The last thing I'd like to say, very quickly, if you let me, just 5 things that are on the horizon for this language, because I think it's these are the key elements that will allow it to be in a sense, a happy partner with BPF. One is the separation of the language from the underlying architecture. It should be important to have code that is portable across a number of different reference architectures. So in other words, that you have a number of reference architectures that are variants on that PISA architecture, and you would expect your code to be portable from one to another. We expect to extend P4 to express packet scheduling and different QoS disciplines. We are aware that there are cross-compilers being developed to and from BPF. I have a long-term aspiration, which is my last slide. I always put this in the slides to remind me of where I think we should be going. You know, we have these network, if you think of that at the bottom there as a pipeline of network from OVS through a network interface card, through switches, a number of switches along a network. This is the pipeline that our packets follow. As networking people, we tend to think in terms of protocols and formats of headers and stuff like that. I encourage you to think a little bit higher than that. Abstract away those details so that we can head towards a world where we declare a network forwarding behavior that we want in terms of an end-to-end behavior to do with security, reliability, congestion avoidance, things like that, where we're describing a behavior that is not about bits and bytes, not about formats of headers, where something else is responsible for partitioning and then compiling that down to that pipeline in a way that most of the time we never need to see. We are quite far from this. We're quite far from this. But if we can do it, then I think that we'll be able to make our networks richer, easier to see what they're doing, easier to debug, and ultimately more reliable. And then we can all go to the beach. Thank you.